सुस्वागतम, नमस्कार, केम छो, आदाबार्स, गुड आफ्टरनून। आप सभी का पीआरएल के अमृत व्याख्यान में स्वागत है, अभिनंदन है। वेरी वार्म वेलकम फ्रॉम मी अनिल भारद्वाज फॉर द पीआरएल का अमृत व्याख्यान। दिस इज द 39th व्याख्यान of the series of 75 of Vyakhyans, which is being organized as a part of PRL's 75 years of legacy and history in fundamental physics and space sciences. Established in the year 1947 by father of Indian space program, Dr. Vikram Sarabhai, the PRL's Platinum Jubilee coincides with India's 75 years of independence. Hence, it's a joint celebration of development of science and technology in India by PRL under the banner of PRL Amrit Vyakhyaan. Today, we have yet another distinguished speaker or Vyakhyaan Karta with us, Dr. Krishnan Raghavan, who is the director in charge at Indian Institute of Tropical Meteorology in Pune. And he is going to give Vyakhyaan on predictive understanding of the Indian monsoon in a changing climate. Monsoon, as we all know, is very important for the country like India, and we are going to hear from him about its predictions and understanding better the monsoon, which in fact affects the weather system and the climate of the India. So with this, I would request my colleague to introduce Dr. Raghavan to all the audience. Over to you.
Thank you very much. Thank you very much, Professor Bharadwaj. It's indeed my honor and privilege to introduce today's speaker and such an illustrious researcher. Dr. Krishnan Raghavan is the director in charge of the IITM and the executive director of the Center for Climate Change Research, CQBAR, at Pune. And with more than 5,000 citations of his cutting-edge research, Dr. Raghavan Krishnan is a world-renowned climate modeler belonging to India. He specializes in climate modeling to understand scientific issues relating to climate change, Asian monsoon, and water cycle, and is engaged in developing in-house capability in Earth system modeling to address the science of climate change. Under his leadership, the CQBAR developed the IITM Earth System Model, ESM, as we all know, the first global climate model from India that contributed to the CMIP 6 and IPCC 6 assessment report. As most of us know, he was a coordinating lead author in the IPCC AR6 Working Group 1 report and the Chapter 8 on water cycle changes, and the drafting author in the summary for policymakers. And he and his team from CQBAR IITM published the first National Climate Change Assessment Report of the Ministry of Earth Sciences, Government of India in 2020. He has more than 140 scientific articles and papers to his credit. He has supervised and co-supervised 12 PhD students already, degree awarded, and 11 more are working under his guidance. He has guided 7 master's dissertation, and he is also well known among the researchers for his lectures in geophysical fluid dynamics and atmospheric sciences. And in terms of adoration of his scientific contributions, he is already member of Joint Scientific Committee JSC of the World Climate Research Program of WMO, and he is also member of the leading advisory committees of World Climate Research Program of WMO and other such bodies. He is fellow of Indian National Science Academy, Indian Academy of Sciences, and also the fellow of Indian Meteorological Society of India. The fact that Dr. Krishnan has scaled this great height in research is in particular a matter of great pride for us, because Dr. Krishnan is an alumnus of PRL. He pursued his PhD research in atmospheric sciences at the Physical Research Laboratory, Ahmedabad. And we are indeed very happy that today he is with us to deliver his talk. So with this brief introduction on behalf of all of us here, I invite Dr. Krishnan to kindly deliver his talk on predictive understanding of the Indian monsoon in a changing climate. Over to Dr. Krishnan.
Yeah, thank you very much, Dr. Deshpande, R.D. Deshpande, for your very kind words and very nice introduction, and Director Professor Anil Bharadwaj for the very warm welcome, and the entire team of people, this PRL Amrut Mahotsav team, for giving me this opportunity. So, good evening to all of you, and good morning, good afternoon to people elsewhere who are witnessing. This is really a great honor for me to be presenting this, and I greatly appreciate this. Thank you very much. And I'm seeing so many of my old friends, Nandita, Pallam Raju, Lokesh, and Bhushit. And also I see Ravi Bhushan and Neeraj Rastogi, Venkat, Ramani, and all in the participants. Very nice. So it's very, very heartening, and I am greatly honored and humbled by this. Thank you very much. So with these few words, I will share my screen. So once again, good evening to all of you. So today's talk, I thought I'll focus on this predictive understanding of the Indian monsoon in a changing climate. So the emphasis is going to be more on understanding. Although we have an ambitious plan of going for prediction, without understanding the monsoon, any prediction is going to be a very, very challenging job. So keeping this especially in the backdrop of the climate change, ongoing climate change, which is further projected to intensify in the coming future. So this challenge is going to be even more severe. So the emphasis will be on understanding the Indian monsoon and how to predict it. So with this plan, I have planned my talk and my heartfelt acknowledgements. I'm very, very happy to be giving this talk in PRL. So my heart belongs to PRL, and I thank the director of PRL and the Amrut Vyakhyaan team and all my PRL friends and colleagues who have always been a big source of inspiration for me. And that was a very important time for me in PRL 87 to 92. That is when I got introduced to this field. And I want to thank all my teachers and mentors, many of them. And I learned a lot from PRL and many colleagues, scientists, staff. And later when I came to IITM and went to also NCMR, WF, and other places, I have been inspired by my students. I've learned a lot from them and postdocs. And I remember the meteorology group because I was not knowing anything in meteorology. So my Guruji, Professor R.N. Keshavamurthy, he was the person from whom I learned. And also Professor Satyan, he was also in the team meteorology group. And my colleague V. Krishna Kumar, who was almost was completing his PhD. Now he is in US. So I learned a lot from them. And Kastureji, who was doing all the programming and modeling. It's a huge experience. So I'm dedicated. I really want to acknowledge my gratitude to the meteorology group of PRL and so many faculty, senior professors, without whose inspiration and motivation, I could not have come this far in life. And all my colleagues also at IITM, PRL, NCMR, WF, IMD, MOES institutions and various places. And I have also had collaborations with various academic and R&D institutions in India, and particularly the Frontier Research System for Global Change, where I worked in the global warming group for 2 years, so it was led by Professor Manabe, who got, in fact, the Nobel Prize in 2021. He was the group leader of the global warming group, and also my mentor, Masato Sugi. So they're all people who have really inspired me. And also I happen to work at various international centers. So my heartfelt acknowledgements for them. And finally, my family and friends. So with this acknowledgement, so as was mentioned in the introduction, I also was a fortunate to be a coordinating lead author in the chapter 8 of the water cycle changes. So it's a new chapter. It's a process-oriented chapter in the IPCC AR6. And we had 3 coordinating lead authors, Hervé from France, myself, and James Renwick from New Zealand, and 13 lead authors. And we had something like 47 contributing authors and 2 chapter scientists. One of the chapter scientists is my own colleague, Dr. Sabin. So it's a big team. So it's a team effort. And so the AR6 working group one came out with some clear messages, both on the attribution and the future projection of the human influence on climate change. So the human influence has warmed the climate at a rate that is unprecedented in the last, at least the last 2000 years. And when we see, this is mainly coming because of the greenhouse gas emissions due to human activities. And when we look at the last 100,000 years, perhaps this is the warmest multi-century period. And the CMIP6 models, there were something like 50 plus models that participated in the CMIP6 exercise, which then feeds back into the IPCC. So this is based on the CMIP6 models. They all did the same experiments. And this black line shows the observed global mean temperature, what is shown in the black line. And the one in brown is the experiments, the CMIP6 models, in which the IITM Earth System model also participated, which has both the influence of human and natural forcings. And so when you include incorporate the human influence, that is mainly through the GHGs, we are able to see this warming trend that we are seeing after the 1950s. And if we had only natural forcings like the solar irradiance and volcanic forcings, we cannot explain this observed trend. There are some episodes of cooling that we see. This is the one that is due to the Pinatubo, which the models are also able to capture, and the previous one due to El Chichon. But the overall warming trend that we are seeing can be explained only if we account for the greenhouse gases mainly, and also to some extent the influence of the aerosols, anthropogenic aerosols. And also this is another very strong statement. The observed warming is driven by emissions by human activities with greenhouse gases, GHG warming, partly masked by aerosol cooling. So if we had only GHG warming, greenhouse gases, the forcing, the warming we could have expected, this is 2010 to 2019 relative to the pre-industrial condition, that is 1850 to 1900 would have been 1.5 degrees only with GHG. But the observed warming is about 1.1. And so there is a net cooling. This is mainly coming from the aerosols, mostly the sulfur dioxide, and also to some extent some organic carbon, and partly some cooling due to the land use, reflectance, and irrigation. So, this net effect, there's a net masking effect of about 0.4 due to the aerosol influence. And so this is particularly important because when we are talking about water cycle, when we are talking about monsoons, we have to keep in mind that it is not only the greenhouse gases, but also the other drivers such as aerosols. And so these are the future projections. In the future, this is again from the multiple CMIP6 models. We have different scenarios known as the shared socio-economic pathways, SSPs. So the SSP 111 is a kind of a very low emission scenario, and the 2 is somewhat intermediate, and the 3 and 5 are high emission scenarios. And so when we look at the low emission scenarios, only in the 119, we are able to limit the warming below 2 degrees by the end of the 21st century. And even in the 245, which is presently, this is something we are very close to following the 245. So the intermediate scenario also, so by the end of the 21st century, this concentration of this carbon dioxide in this is somewhat like doubling to the relative to the pre-industrial values. So the likely range is about 2.7 increase in the global mean temperature. And so clearly we are crossing the 2 degree even with the 245. And with the 370 and 585, these are much, much higher. So the values are more than 4 degrees, close to 5 degrees in the 585. So the main message is global warming of 1.5 degree and 2 degree will be exceeded during the 21st century, and 1.5 degree will be exceeded in the next 20 years. And unless deep reductions in carbon dioxide and other greenhouse gases emissions occur in the coming decades. So these are the projections. So now what does it mean? We also had in the water cycle chapter assessments of the monsoons, all the regional monsoons. In the AR5, in the fifth assessment report, the assessment was about the global monsoons, which is defined as the global monsoon as the area which is shown by this black contour. That is the area where with local summer minus winter precipitation exceeding 2.5 millimeters per day. And this definition includes many of the regional monsoon areas within the global monsoon, but it also includes several oceanic areas and some areas, for example, in South Africa and Equatorial America, which we cannot really categorize them as monsoons. They are associated with strong seasonal cycle of precipitation, but we cannot, it's not clear whether we can call them as monsoon regions. So in the sixth assessment report, we have these dotted regions over Equatorial America and South Africa, we don't call them as monsoon region. We do have an assessment of seasonality in the precipitation changes. But the other regions, we have a South Asian monsoon shown by the pink region, and then we have the East Asian monsoon shown by the purple region. We have the Australia maritime continent, the West Africa, the North America, and the South America. So 6 monsoon regions. So the main assessment is that the global land monsoon precipitation, it decreased from the 50s to the 80s, 1950s to the 1980s, partly due to the anthropogenic effect of the anthropogenic aerosols, mainly in the northern hemisphere, but has increased since then in response to GHG warming, because greenhouse gases having a longer lifetime, they are there for several, they can be there for a couple of centuries and even beyond. And these are long-lived forcing. And so their impact we are seeing even now. And there is also a large-scale multi-decadal variability in the precipitation changes. So this is a medium confidence statement. And in the 21st century, the global land monsoon precipitation, especially in the northern hemisphere, is projected to increase in response to GHG warming in all time horizons. Especially if we cut down the anthropogenic aerosol emissions, the projections indicate that the precipitation is going to, monsoon precipitation is going to increase. And in the long term, global monsoon rainfall change will feature a robust north-south asymmetry, characterized by greater increase in the northern hemisphere than in the southern hemisphere, and an east-west asymmetry characterized by enhanced Asian-African monsoons and weakened American monsoons. So basically, Asian and African monsoons are projected to increase in the future, especially in the middle and long term. And so this is some kind of a box whisker plot of the observed and observed trends in the precipitation. This is 1951 to 2014. So left panel is for South and Southeast Asia, right panel is for East Asia. We have shown observations from 3 different data sets, the Aphrodite, CRU, and GPCC. Over South Asia, we can see a decreasing decline in the precipitation for this period. And these are the different CMIP-6 model experiments from multiple models. And so the historical all forcing experiment, when we have GHG, aerosols, land use, land change. So these from the multiple models, we can see the median from all these models indicating a decrease in the precipitation. So the South Asian monsoon precipitation decrease, which we are seeing in the observations, can be explained by this by all these human influence. If we had only natural forcing, we are not able to, the blue whisker, we are not able to explain this decrease. And when we have only greenhouse gas, we see that there would have been an increase in the precipitation. With only aerosols, it is the opposite. It would lead to a decrease in the precipitation. So we can see the contrasting signatures of the aerosol and GHG forcing. And in the all forcing experiment, historical forcing, we are able to see this precipitation decline in the observations. And so that is for the South Asia. Similar thing we also see over the East Asian region. We do see a lot of decadal variability, and the magnitude of the decadal variability is kind of underestimated in the models. That is something we have to keep in mind. And with regard to the future, these are the future projections. We have 3 periods, 2021 to 2040, we call it as the near term, and 2041 to 2060 midterm, and 2081 to 2100 the long term. And we are showing for 3 different scenarios. The 126, that's a low emission. This is the intermediate SSP 245. SSP 585 is the high emission scenarios. We see that especially in the middle and long term, very clearly we can see an increase in the monsoon precipitation for South Asia and also for East Asia in the middle and long term, very clearly in all the scenarios. In the near term, you can see that there is an uncertainty in the near term, especially both for the South and East Asian region. And this uncertainty comes because of the internal variability largely, and also by possibly due to the effects of natural forcings like volcanoes, which I will be touching in my talk. So the point that we have to keep in mind is, although we are projecting that monsoon is going to intensify in the future, there are uncertainties widespread across the models. And how do we deal with it? And so one of the things is that all the CMIP6 models, they have improved for the CMIP class of models. When we start from CMIP3, which was in 2004, then 2007 assessment, AR4 assessment used the CMIP3 models. Then we have the CMIP5 in 2013 in the IPCC report, and now we have the CMIP6 models. So consistently all through, the CMIP6 models have exhibited a low precipitation bias, a negative precipitation bias over the South Asian region. This is from the CMIP6 multi-model precipitation. This is for the period 1985 to 2014. So when we compare against the observations, the models are kind of underestimating the precipitation over the Indian region. This is a multi-model mean. And also, although there is a slight decrease in the bias, by and large, the dry bias in the models have continued. And this is one of the big concerns. And there is an increase in the precipitation over adjoining oceanic areas and over the Himalayan foothills and so on. And so the problem is, once we introduce a bias in the precipitation or the rainfall, it is going to affect. What it implies is the latent heat of condensation. We are having a problem with the latent heat of condensation. And once there is a problem in the latent heat bias in the systematic error in the latent heating, it will affect the circulation. It can introduce as bias errors in the large scale tropical circulation, particularly in the tropics. And so if we introduce biases in the tropical winds, it is going to affect the sea surface temperature, large scale sea surface temperature gradients. So we are going to propagate these biases from the atmosphere to the ocean and across different scales of the Earth system components. So this is going to, we are entering a vicious cycle of bias propagation across scales and across ESM components. So an important urgent need is to reduce the biases in the monsoon and tropical precipitation. And that is a very important thing that we have to focus. And how do we reduce? So big question is for the coming, this is also in the WCRP, how do we reduce the systematic errors in the climate models? What if, so there is no clear solution. People are working, this is a research problem, ongoing problem. So do we have to go for very high resolution cloud resolving models? Answer is not. Some people think this may be the approach. And there's another school of thought that thinks that we have to go for new techniques, data-driven techniques like AI/ML techniques for improving the convection parameterization and so on. So there are no ready answers. So I will be basically talking about how do we reduce the uncertainties in the projections of the regional monsoons. And basically, I want to focus on what is known as the predictive understanding. We have to really understand the phenomena of the monsoons and the extremes if we want to really reduce the bias in the model projections. So that is the key. So that will be the focus of my talk today. If we want to really improve the models. So the sources of uncertainty, we have different sources of uncertainties in the models. This is also assessed in our chapter. So it can come from the model response uncertainty. So we saw large intermodal spread in the range projected by the set of climate models. There could be uncertainties because of the way in which we represent the physical processes, mainly the atmospheric convection. There are also the effects of aerosols and clouds, cloud microphysics, how they interact. And this can be important for the clouds and precipitation processes, especially the warm rain processes. That is also which happen in the monsoon environment. There are uncertainties in the land surface processes. And by going to high resolution models and convection permitting models, we may get some value additions, but it's not clear how much we will be able to reduce these uncertainties. And then we have uncertainties coming from the internal variability and also natural forcings like volcanic eruptions. Because big eruptions like the Pinatubo, which happened in 91, 92, around that time, and also if that is supposed to happen in the coming decades, so that's an unpredictable natural forcings, and that can lower the degree of confidence in projecting the water cycle changes, including monsoons, especially when we are talking about the near term. And there are also non-linearities across the global warming levels. So when we go from 1.5 degree to 2 degree to higher warming levels, so the precipitation doesn't scale linearly. So there are non-linearities coming because of the atmospheric circulation dynamics and also even the precipitation processes and also land surface feedbacks processes like runoff, groundwater recharge, snow melt, soil moisture, evapotranspiration. And there is also a potential for abrupt change because especially in the North Atlantic, there's a lot of melt of both the Greenland ice sheet and also the sea ice. And this can weaken the deep ocean circulation known as the Atlantic Meridional Ocean circulation. And also already people are seeing the signatures of a weakening of the AMOC. So the question is whether there can be a collapse of the AMOC. If this can happen, then there is a potential for abrupt change. But what the assessment says is it's very unlikely the AMOC will collapse during the 21st century. But if it were to collapse, then we can expect major changes, abrupt changes in the water cycle, as well as the effects of Amazon deforestation or the effects like the greening of Sahara and Sahel, dust emissions due to land use changes and so on. And finally, we can have uncertainties due to the scenario itself. So I will mainly focus on what are the sources of uncertainty, how we can address some of the uncertainties by improving the key monsoon process, especially the atmospheric convection. I will focus on that. And so this is especially important when we are talking about organized monsoon convection and the cloud systems. Because in the summer monsoon time, we have many mesoscale convective systems of the scale of a few hundred kilometers, but they can organize over very long spatial scales of several thousands of kilometers. And these organized systems, they're a very enormous source of latent heating and precipitation. So at present, many of the models are having problems with the latent heating. And this is introducing biases in the tropical circulation and the monsoon circulation. So important thing is how do we deal with the organized convection and the mesoscale systems? And this has implications for the movement of the ITCZ and the tropical rain belts. And also there are issues related to aerosol cloud interactions, the warm rain processes in monsoon convective areas. So there are multiple approaches people are thinking. One school of thought thinks that we need to go for kilometer scale, about something like a horizontal scale of about 1 kilometer, which is going to be computationally impossible, almost very, very difficult to only very few centers in the world can do this. And now there are other groups, there's an alternative thinking that we have to go for new developments such as AI and ML techniques for extracting patterns using geospatial data. Now we have, based on observations and model simulated big data, especially due to availability of huge amounts of satellite data. And there's other group that is thinking of model hierarchies. You need not one model, or you need a hierarchy of models of different complexities, with models from more simple models which are easy to understand, and models of intermediate complexities, and models of even more detailed sophistication and so on. So you need a hierarchy of models to address this. And then there is another school of thought, especially by Kerry Emanuel, professor at the MIT, and his view is that we need to have a more balanced approach for advancing basic understanding by combining theory, observations, and models. So the emphasis is on understanding. So I'll be focusing on the last two. So basically, when we talk about the modeling, I'll just quickly go through the physical. We are basically looking at the physical principles that govern the atmospheric flows, and we go back to the classical momentum equations originally proposed by the Newton laws, the momentum equations, and we have the thermodynamic energy equation, the first law of thermodynamics for the energy conservation. We have the mass continuity equation for the mass conservation, and the hydrostatic balance, the hydrostatic equilibrium. So in a large scale, the atmosphere is usually in a hydrostatic balance. And we have the water vapor equation, mass continuity equation. And on the right-hand side, we see this shaded, shown in colored. So these are kind of harmless looking terms. And this is where the real challenge is. How do we represent the friction in the model or the heating in the model in the thermodynamic energy equation? Or how do we account for the water vapor sources? The sources of precipitation and evaporation, and and the runoff and so on. So these terms are basically parameterized in the model. So these are subgrid scale processes. I'll be coming to that. So when we want to solve these equations, these are basically numeric. These are nonlinear differential equations, partial differential equations. And they are basically governing the rate of change of temperature, pressure, velocities, humidity, etc. And we normally discretize them using the finite difference method on the grid points. And when we make the grid finer, obviously the resolution is going to increase. And we have many vertical levels in the atmosphere. So typically tens of millions of computations happen, and the time step is typically about 10 minutes. So once we increase the resolution, the time step, the grid size becomes smaller, the time step also becomes smaller, the computations are going to increase. And typically the present day, the climate models are something like 100-kilometer grid. And of course, there are in the horizontal resolution, and some models are even running at 50 kilometers. And so over time, we have improved in terms of resolution, and we are having more vertical levels. And similarly, we have even in the ocean. I'm not going to that. So we have a ocean circulation model, and many levels in the ocean are also for the cryosphere. So when all these different components are integrated, we have an Earth system model. And so it is computationally very, very intensive. Now the question is, when we want to represent processes that is happening within a scale of a grid, we call them a subgrid scale processes, and how to represent them. And so normally the physical process of importance for the weather prediction and also for climate are, for example, how to treat deep convection or the shallow type of convection, or how to represent the long wave radiation, both the long wave and short wave radiation. So because they are interacting with the atmospheric constituents and the absorbers and the scatterers. And also, how do we represent the fluxes of latent heat or sensible heat flux, and also the radiative fluxes, and also the turbulence, and also the orographic effects and atmospheric chemistry. So these are not explicitly resolved in the current models, but they are represented in terms of the large scale variables. So which we call them as parameterization. And that is where we are having challenges. And what does it mean for the Indian monsoon? I'll be briefly touching upon that. So the Indian monsoon in a conceptual way is basically, we can look, it's a coupled phenomena where the monsoon circulation and rainfall, that is basically the latent heating. So when the clouds are condensing, they produce an enormous amount of latent heating. Now, thanks to the satellite data, we are able to have estimates of the latent heating. And this is very, very important for the tropics. So the monsoon, to begin with, we have a thermal contrast. Right now, we are seeing the land getting heated up over the Asian landmass, and the oceans being at a relatively lower temperatures. The thermal contrast is an important trigger for setting up the circulation, because it sets up the pressure gradient And once with the pressure gradient is set up, then the monsoon flow develops in response, and also under the influence of the Earth's rotation, you have the cross-equatorial flow developing. And once a monsoon flow is established, this is going to pick up a lot of moisture from the Arabian Sea and from the Indian Ocean, and also from the Bay of Bengal. And when it interacts with this Western Ghat orography and also the Burmese mountain, it's going to form clouds, and these clouds are going to produce enormous amount of latent heating, which in turn maintains the circulation. That is the key point. So there is a feedback between the circulation, the latent heating, which sustains the monsoon through the entire season, June to September. And of course, we do have year-to-year variations in the rainfall, which can be influenced by drivers like El Nino Southern Oscillation or the Indian Ocean Dipole. These are all different modes of climate variability they can affect. And also external drivers like the anthropogenic forcing due to greenhouse gases or aerosols, and also volcanic forcings. So these are all the important drivers of the monsoon. In fact, the importance of heating, this is a very early work which I was introduced by my Guruji for my PhD by Adrian Gill. So he used a very simple model. This was in Quarterly Journal of Royal Meteorological Society. So he conceptualized the model. This is using a very simple shallow water equation system. And earlier Matsuno had derived that you can, in the tropical atmosphere, you can excite many of these very long waves like the Kelvin wave and the Rossby wave. They are very important for explaining the dynamics of the tropical motions. But what Gill did in 80 was, if you have a forced response, if you prescribe heat sources, and if you have a damping term, you will be able to simulate a monsoon type of pattern. That was, and also the tropical, we have the Walker circulation. So typically, if you have a heat source that is a symmetric type of heating, let us say over the Indonesia or the maritime continent, we can generate a kind of very large scale Walker circulation, which is basically a kind of a Kelvin wave response and a kind of off equatorial Rossby wave response. This is a type of a symmetric heating around the equator. But if you have a heating that is off the equator, if you have a heat source, typically like the South Asian monsoon, a heating over the South Asian region, and more of a radiative cooling in the southern hemisphere. So you have a dipole type of pattern. With the simple heating, he could generate a monsoon type of pattern to the west of the heating. And he used a very clever long wave approximation by dropping this term. And so what the important message that he conveyed was in this, that the monsoon circulation can be represented as a response to heating. That was the main message. And now we have much more understanding, and but basically monsoon is much more complex than that very simplistic picture. There are different scales that are involved when we are looking at the monsoon. We have a very large scale monsoon that is set up by the thermal contrast, development of this large scale flow, which is the pressure gradient. And then within the season, we have these cloud bands moving slowly from the equator towards the north, the movement of the rain belts, something like a 1 degree per latitude per day. And they have a kind of time scale of about 30 to 60 days. This is a kind of low frequency variation. And then we have also having various synoptic systems, like the low pressure systems, the depressions that form in the Bay of Bengal, and also the Mytropospheric Cyclones that produce rainfall over Gujarat, Maharashtra, Western Maharashtra. And so these are all very important rain producing systems. And so these are associated with organization of several mesoscale system and embedded deep convective systems, and they can produce very heavy rainfall also. So there are different scales involved when we are talking about the monsoon. So there are so the interactions of these scales are going to be very important. And so the question is, under changing climate, how is this going to? So we have to understand how climate change is going to influence these multi-scale interactions. And this is a very important schematic of Krishnamurthy and Balme in 1976. In this low level, we have the very strong cross-equatorial flow. But once we have this convection developing and deep clouds forming, so in the upper level, you can have a very strong outflow. And we have a major anticyclone known as the Tibetan anticyclone, the Tibetan high. And there is a strong outflow, and there is a very strong easterly jet. It is known as the tropical easterly jet. And what he noted was, if you have this simple A north-south meridional type of picture where you have a deep convection happening over the South Asian region and a sinking over the southern hemisphere, and you have a meridional overturning circulation. And he postulated that this can be driven by a kind of radiative convective feedback. And what he showed in this simple model is that you have various elements of the monsoon system, like the monsoon trough or the Mascarene high, and also the Tibetan high or the easterly jet. They all exhibit a quasi biweekly oscillation, something like a 10 to 20 day oscillation. And as I said, in the upper troposphere, in the upper level, we have a very large, strong anticyclone. This is at 200 millibar, something like 12, 13 kilometers above this surface. And this is the region of the strong easterly flow. And you can see the easterly is extending all the way from the Asian region into the African continent and further westward into the Atlantic. And this is truly a global scale feature, a planetary scale circulation feature. It's a kind of a wave number 1 or wave number 2 type of pattern. So over the upper level, upper troposphere, you have the mid-oceanic ridges and 2 anticyclones, very large scale anticyclone. Why this is important is the core of this anticyclone is located right over Uttarakhand. And any major fluctuations in this anticyclone, if this becomes unstable, it can produce extreme events like the 2013. I'll be discussing that. And the point is that the key heating is the latent heating is a very important source for driving the tropical circulation. So winter time, we have the heating residing over the maritime continent and other areas. And these are the storm tracks that we are seeing. So I've just put the 90-degree longitude just to understand the location. And this is based on Hoskins' calculation based on the ECMWF reanalysis. So the heating he computed as a residual from the time average thermodynamic energy equation. And you can see the major heating in this during winter time located over the maritime continent, over African region, and over South America. And in the north, you can see the storm tracks. And the areas of cooling, negative values where we are seeing that they are associated with mostly radiative cooling. And when you come to the summer monsoon, June, July, August, you can see the heat source has moved towards the South Asian landmass. It's a main heat source. And also we see some heating over the American monsoon or the Central America. And so the heating is going to be the primary. And earlier, we did not have these estimates of observed estimates of heating. And this was computed from the reanalysis as a residual of the thermodynamic equation. And now with the availability of the TRIM satellite data, especially where they have the precipitation radar, they are able to construct the 3-dimensional structure of the hydrometeors and the crowd reflectivity. We are able to get the estimates of the latent heating. And this is from the latest version of the TRIM PR data. This is by Shige et al. You can see the rainfall very closely hugging the west coast. And this is a region of very deep, very strong heating, latent heating. And this is a strong heating that you get over the Myanmar coast. And this is with the earlier version of the precipitation radar data. Now this is the latest version. We are having something at a 5-kilometer grid. And so we can see that this is from the over the west coast. Sorry, this is over the Myanmar coast. This is the peak in the rainfall, the dotted line, and this is the orography. So the maximum rainfall you can see is located on the windward side, especially over the Myanmar coast. And whereas over the Western Ghats, it's more gentle. It is very closely aligned with the orography itself. And now also, as I mentioned, because of the availability of the precipitation radar data, we are able to understand different forms of clouds, where very deep clouds, convective clouds, what you see typically in thunderstorms and very deep convective clouds, and also more large-scale cloud cover, cumulus clouds, and these are nimbostratus clouds. They are not really very shallow stratus clouds, and they have a vertical extent of 8, 9, 10 kilometers, and but their horizontal extent, it is called in the literature as the stratiform, and the horizontal scale can be much more widespread as compared to the convective scales. And so typically the convective clouds from the radar echoes, they're able to classify the convective as more as young and active convection, and vertical velocities are very high, several meters per second. And whereas the stratiform clouds are generally older forms of the cloud, and they have less active convection and vertical velocities are much lesser. But the stratiform clouds have a much larger horizontal scale. But the key point is that the heating pattern, especially the vertical structure of heating, is very, very different in the two. These people have studied extensively. Typically, for a convective type of cloud, you have a single peak. You have minimum heating at the lower and the upper levels, maximum heating at the mid-troposphere at around 500 millibar. But when you look at the stratiform heating in the lower levels, typically what you see in the monsoon regions, you don't see much very deep heating, very high values of heating in the lower levels. And whereas when you go in the middle and upper troposphere, especially above 400 millibar, you get the maximum heating. So these are top heavy clouds, and the profile of heating is very, very different. And with a different form of vertical heating, your circulation response is also going to be very different. And this is a new knowledge that we are understanding because of the trim precipitation radar. And now we have a good understanding of the statistics of the stratiform and convective contributions. And now generally what is understood is during the summer monsoon time, the stratiform population is much higher over the Bay of Bengal and eastern part of India. And this is very important for the monsoon systems. So it also affects, because the structure of heating is very different. In this paper with my colleague Ayantika Chaudhary, we had studied what will be the impact of this heating on the monsoon trough, which is a very important dynamical feature. So depending on whether it's a convective type of precipitation or latent or stratiform type of precipitation, how does it affect the monsoon trough dynamics? And so we looked at several active monsoon cases, and what we find is during the active monsoon, the trough can almost up to 300 millibar. Compared to the climatology, so the cyclonic vorticity over the monsoon trough can be much, much higher. So this is the wind anomaly at 500 millibar. You can see a very large scale trough, but in the vertical extent can be much deeper during an active monsoon. And the reason is, and when you look at the scale of the convection, this is from the trim precipitation. This is a composite of all the active monsoon days based on the Rajivan et al. Data set from the trim 3B42 data. You can see the rainfall extending the extent all the way from the western part of India, northwest India, extending into Southeast Asia, almost into the South China Sea and the Philippines area. So a scale of about 3,000 to 4,000 kilometers. And within this ITCZ, so the ITCZ has really moved north, and with this large scale organized convection, it is associated with many embedded mesoscale convective systems that is organizing to produce this system, very large scale organization. And we have to keep that in mind. And we also estimated how much is the heating. This is the vertically averaged heating, the mean heating during the summer monsoon time based on the trim data. And we also have this vertical structure of heating. This is a cross section that we are showing between 10 to 20 degree north. We can see much of the heating maximum is around 400 millibar. So these are very deep clouds, and that is where the heating is concentrated. And then we use this very simple model. In fact, this model, the origin of this model goes back to PRL with Kasturi doing all the development. And we have added some more refinements, added more levels, and learned how to incorporate these different forms of heating. And when we tried to produce this, with the climatological heating, when we applied on this monsoon, we can see a very nice cross-equatorial flow. You can see this this is at the lower troposphere, a very nice cross-equatorial flow. This is the monsoon trough, the subtropical high in the southern hemisphere, and in the upper troposphere, a very strong Tibetan anticyclone and a very strong easterly jet. And you can see also the planetary scale structure. Now, and then we also did a further experiment. We took the case of active monsoon, where I showed the example of the organized convection. And we assume that the cloud in this, the anomalous rainfall that we are seeing we assign different values of stratiform and convective precipitation. In the experiment 1, we had 0% stratiform and 100% convective. And gradually, in the experiment 2, the stratiform was increased to 30% and convective to 70%. And the experiment 3, 50-50. And in the experiment 4, it was 70% stratiform and 30% convective rain. And then what is this? So as we gradually increase the stratiform rain fraction, you can see the heating anomaly, the maxima, the position of the heating maxima also gradually elevates. And once the heating maxima we are elevating, it has a very important implication on the mid-level response. So if you have 70%, just to give an example, if you have only 70% of convective clouds, what it says is the mid-level response will be very much localized. We have to keep that in mind. But if you have a 70% stratiform, which is much more widespread, the circulation response is a much, much wider horizontal scale. It's extending almost into the West African region. So with the same rainfall, how you distribute is very important. So in the vertical, and because once you have this more of stratiform heating, the vertical gradient of heating becomes very large over the mid-latitude, over the mid-levels. And because of this strong gradient of heating and maximum heating in the mid-troposphere, you have more convergence, and this stretches the vorticity at above in the mid-troposphere and also in the upper troposphere. So the circulation becomes stronger. Even the upper troposphere anticyclone becomes very strong. That's an important message. And the way I'm saying this, unfortunately, many of the models, this is a paper by T.N. Krishnamurthy et al. They looked at the estimates of profile, vertical profile of Q1, and from different models, they used different parameterizations, and they looked at the cases from the TRIM PR precipitation radar data for the day 1 forecast. And clearly what they found out, the models are having errors. Even in day 1, large errors in the vertical structure of the model-derived latent heating. So once you introduce errors in the latent heating, the placement of the maximum heating is having an error. And then this leads to errors in the convergence and divergence centers. And then you have problems in simulating the synoptic and large-scale circulation response. So this is a very fundamental problem. And this now we are seeing this even in the CMIP6 models. I'm not going to those slides. So clearly, if you want to simulate the extremes, precipitation or extreme events, it's very important that we get the latent heating clearly in the model, which means we need to really improve the parameterization of convection. And why I am saying this is now when we look at some of the extreme events need not be caused just by local effects. Local is one thing, but they can be global drivers. Although the impacts are regional, they can be influenced by global drivers. I'll be showing some examples. This is the example of the Uttarakhand rain event, June 2013. Many stations here received rainfall, in just one day rainfall, more than 200, 300 millimeters, and some of them even 400 millimeters. And we looked at, this was by my colleague Vellur et al. He looked at a composite of 34 heavy rainfall events for the same region, over the Uttarakhand region. And the question is, so when we want to understand extremes at a regional scale and how climate change is going to affect and how it is, and how to predict them, we have to also, first question is we have to understand them first. So this is an important paper. I thought I should, when I'm talking about predictive understanding, I should mention. They say that in general, the development of an extreme event depends on a favorable initial state, the presence of large-scale drivers, as well as positive local feedbacks and stochastic process. So it's not only the local effects, also it can be influenced by large-scale drivers and also stochastic, so random processes they can affect. So a better understanding of the drivers and processes will improve the prediction of extremes and support process-based evaluation of representation of weather and climate extremes in the climate model simulations. So this I thought I should mention. This is especially important not only for heavy rainfall and flood, also for heat waves and droughts. And so coming to the example of the Uttarakhand event, So during this time, the Tibetan anticyclone, which I mentioned, became highly unstable. It was very, very active. So the scale of this anticyclone extended westward, and it started kind of wobbling, and the westward extent of this anticyclone extend. And around the same time, there was a kind of a very deep trough extending from the mid-latitude, in fact, from the very high latitudes, from the polar regions, a very deep north-south trough. Very slowly it was moving, and it coincided. And at this time, there was also a low-pressure system moving from the Bay of Bengal very quickly. So May 16th, this was the time, almost like an onset, the monsoon onset took place, which was very, very early. So there was a rapid movement of the low pressure system. The anticyclone became highly unstable, and there was this deep trough extending from the mid latitude. And so the interaction of this system, as I said, many stations recorded rainfall. This is the 24-hour precipitation accumulations. We can see many stations exceeding more than 370, 400 millimeters of rain in 24 hours. And so the question is, the source of moisture came. This is by Robert Howe's group. It shows the propagation of a low pressure system, which basically brought the moisture. This is from 15th, 16th, and 17th of June. So this 13th, 15th, and 17th. You can see the movement of water vapor clearly from the Bay of Bengal. So the low pressure system taking. Also, there was a substantial amount of moisture coming from the Arabian Sea as well. And this deep mid-latitude trough kind of anchoring there. And the interaction of this led to the convergence of water vapor in that region, a strong convergence, and triggering flaring of these heavy precipitation events. Why I'm saying this, water vapor is a very important source. And now with climate change, with every warming, 1 degree warming, water vapor is going to increase by about 6 to 10%, and typically by about 7%. This comes because of the temperature dependence on the saturation vapor pressure of saturation vapor pressure. So one of the direct consequences is that increases in the water vapor, it has direct, due to global warming, will have increase in the frequency of heavy precipitation, frequency and also the severity of the heavy precipitation, intensity. And so in a warming world, if the same type of event were to happen, impacts would be even more profound. Now another example I wanted to share with you is the Leh flash floods. This was in 2010. Just then, a week after the catastrophic heavy precipitation in the Indus River of Pakistan in late July 2010, there was a different type of precipitation in the city of Leh, India, 500 kilometers to the east. And this was a high elevation region. And also it's like it's a kind of desert type of environment. So in this region, heavy precipitation, torrential rains delivered to the region was by a succession of mesoscale convective systems. So these MCS were the ones that triggered this heavy precipitation and flooding. And this was also the mechanism is that during this time also there was a low pressure system moving from the bay. That was once they were moving. At the same time, this study by Rasmussen and House looked at the satellite images. They noted there's a very strong diurnal variation of convection over the Tibetan plateau. And these MCS, which developed in the afternoon, they started moving westward. And this coincided with the movement of the low pressure system from the Bay of Bengal. And when there was substantial amount of water vapor in that region, it triggered these heavy precipitation events. So basically you have the movement of moisture air and the mesoscale system from the Tibetan plateau, and they can trigger this very heavy precipitation event in the Leh Ladakh region. And so question is, in future, how they are going to respond with climate change. The other important class of events which I thought I will focus on is in the Western India, primarily Gujarat and Maharashtra. This was again what are known as the Mytropospheric Cyclones. This was first identified by Miller and Keshavamurthy during the International Indian Ocean Expedition. And the MTCs are basically, you don't see the surface signatures, Mostly the vorticity is seen at the in the Mytropospheric levels, maximum around, this is what they documented, at 700 to 500 HPA, and the horizontal scale is about 1000 kilometers, vertical scale is about 6 to 8 kilometers, and they noted strong mid-level convergence and upward velocities. And they also noted in the lower levels, it is a cold core structure, the temperature structure. Above, it was a warm core structure. And these MTCs, people did not look at it much later. And subsequently, we had a study again by my colleague. And now with the new data from the TRIM and the GPI, we are seeing that some of the heaviest 3-day precipitation accumulations exceeding 300 millimeter over Western India, and this is during 1998 to 2007, they all happened to somewhat coincide with MTC events. And you can see this event during 2005, something like 3-day accumulation of 700 millimeters of rain, and the other one 650. So these are all big events. And this is a typical example of 2006 from the Meteor satellite, Meteosat 7. So you can see these systems, MCS developing in this region, producing very enormous amount of precipitation. And so the point is, you don't see the surface signatures. So the circulation is basically located somewhere in the lower and in the mid-tropospheric levels. But sometimes they can be aided by the low pressure systems from the Bay of Bengal also. And the important thing is how to predict them. And we also looked at the heating data, the TRIM heating data. They turn out to be more like a stratiform type. There's several cases of the TRIM passes we looked, and over the Arabian Sea and the Western Ghats. Typically, they are associated with this elevated deep heating. And what we found was enhanced heating above 600 millibar, with heating maxima about 400 millibar. And there was also some large scale features like the northward movement of the ITCZ. So the rain bands were moving, the organized convection was moving from the equator to the north. And they were producing this organized convection produced descent over West Asia, over Pakistan and adjoint areas of the surface heat flow. You can see this in the half molar, you can see the propagation, northward propagation of the cloud band. And that is when, this is the period when these MCS develop over this coast, west coast. And so you have this slope northward propagation of the rain band. And this is, of course, producing descent and dry conditions over West Asia. And as these cloud bands, large scale organized band is moving, these MCS can develop. And these MCS have a typical heating, maximum heating at about 400. These are mostly stratiform clouds and associated with heating around 400 millibar. So you can see a positive gradient of heating. So in the vertical, so once you have this positive gradient of heating, you can get maximum convergence at the mid-tropospheric. So heat convergence is maximum at the mid-tropospheric levels, and that is what leads to the formation of the MTC. And the question is, so we could understand, we understand how these MTCs are forming. Now the question is, in a future warming climate, what are its implications? How these MTCs are going to affect? Other drivers could be through remote influence. One of the drivers could be the Arctic sea ice. Now, this is reducing very fast. They are telling in maybe by another 40, 50 years, Arctic would be practically ice-free. And this is a big concern. So one of the implication is that if due to the change in the Arctic is, so normally when you have when it is ice covered and this polar air is cold and it is well separated and you have a very strong jet stream in the mid latitude, so the polar air mass is well separated from the mid latitude and the tropics, and you have warm air in the south. And but once the ice starts melting, the problem is what will happen is the circulation, the atmospheric circulation that descends over the polar region kind of weakens. So you are basically disturbing the temperature gradient between the polar and the mid-latitude region, and this polar vortex starts meandering. So you can get these big meanders. So the jet stream will weaken, but it will have more waviness. And people have shown that this waviness in the jet stream can lead to extreme temperatures in the mid latitudes and also over low latitudes. For example, there were this it also leads to what is known as atmospheric blocking. So, hello, yeah, just a minute. Yeah, so it can lead to these very extremes in the temperature and also in the precipitation. So the question is, what is it? How is it going to affect the tropics and the monsoons? And we also have to deal with natural forcings and internal variability. I'll quickly go through. A large volcanic, why is this? Because as I said, these big eruptions like Pinatubo, these are not due to anthropogenic influence, but they can have substantial radiative impact. And because of the aerosols which enter the stratosphere, they can reside there for a couple of years. And now what models are showing and even observations are showing is that typically after a year, after major large volcanic eruption, this can lead to a El Nino-like pattern. And then El Nino in turn can influence the monsoon. So large volcanic eruptions can be a source of natural variability. So why I am saying is this Enso is an important source of internal forcing that can affect the monsoon, as a mode of variability that can affect the monsoon rainfall. And earlier there was a paper by Krishna Kumar and team who noted that the El Nino monsoon relationship has been weakening in recent times. And subsequently, this was a paper by Marwan and Kurth, where they looked at what they suggested. If you want to look at two oscillatory systems like El Nino and monsoon, you cannot just look at their amplitude variations. You have to look at also their phase relations, how their phases are varying. And what they found is, when you look at the phase coherence analysis of these two systems, they found that in some epochs, some decades, they will be highly coherent. So the phase so you can see these plateaus where there is a very strong coherence, and then there are epochs where there's phase coherence is less. And what they argued was some of these epochs there where there's a phase coherence were preceded by big volcanic eruptions. This was the Krakatoa event, and likewise this is the Agang and so on. So their logic is, they hypothesize that if you have big eruptions like the volcanic eruptions, so through the volcanic aerosols, it can introduce phase coherence of the two oscillatory systems. And we wanted to check this, what is the role of volcanic eruptions on the Enso Indian monsoon coupling. And this was a paper by my colleague Manmeet Singh and team, where we did several large ensemble experiments, and we also analyzed paleo data and several other data. And what we find is, indeed, big eruptions like the Krakatoa or Pinatubo, they can, and this we also found, we also looked at coupled models from the paleo model intercomparison PMIP data. So indeed, big eruptions have a big role in the phase synchronization of Enso and monsoon. And typically what we find, we tried with different initial conditions. We made simulations of large ensemble simulations with the IITM Earth System model. And we found that typically a year after a volcanic eruption, the El Nino and monsoon tend to synchronize. And you tend to get a El Nino-like pattern in the SST after a big eruption. And then this leads to a kind of, it also influences the monsoon precipitation. In addition, the volcanic aerosols, they have a radiative cooling of the Asian continent, which also reduces the monsoon precipitation by shifting the ITCZ southward. I'm not going into the details. Now, with climate change, how El Nino itself can change this mode of variability, people have suggested that typically with global warming, we should get more of a El Nino-like warming. This is what is the suggestion. The likely mean conditions under climate change, this is based on the CMIP-5. They project that El Nino would lead to a more like a warming like, it would lead to El Nino-like warming in the Pacific because of the changes in the ocean atmosphere feedback. But this has been now, there's a different view again coming from a group from the Lemont, What they are arguing is, although the CMIP models are projecting that with climate change, you should get more like El Nino, like warming, the observations don't indicate. And this has been a big problem. And this is due to the problem in the coupled models in simulating the cold tongue changes in the sea surface temperature of the cold tongue of the Eastern Pacific. So there are these big uncertainties which we need to address. And also, in addition to El Nino, it's also the Enso, also the Indian Ocean dipole, which is an important source of mode of variability. And interestingly, many of the recent wet monsoons like the 1994, 1961 and 2019, very recently, were all associated with positive IOD events, which try to transport water vapor from the Indian Ocean, especially from the Eastern Indian Ocean, and favor the precipitation increase over the monsoon trough region. So we need to really understand these issues. So this is my last slide. So monsoon variability and change, it's basically a multi-scale interactive phenomena, and the prospects for improving monsoon predictive capabilities in a changing climate, we need to reduce the uncertainties in the projections. This means improving the representation of convective MCS mesoscale convective systems, primarily the latent heating, the warm rain processes, the orographic precipitation, mid-level circulation, as well as aerosol cloud interactions, and also the representation of large-scale SST gradients, sea surface temperature gradients, like the Enso or the IOD, because they are fundamental regulators of the tropical and regional precipitation. This is important for not only the mean, also the variability and extremes, because they influence the heat and moisture fluxes and the convective activity and large-scale circulation. So we need to go in for a process and predictive based understanding. No doubt we have to enhance our early warning systems through observations, radar, satellite, balloon, and improve our data assimilation and of not only the circulation and also the vertical structure of the winds, water vapor, clouds, and convection. Go for high resolution models, adopt new techniques for improving the physical process, including AIML, and also combining observations and models, but not only the atmospheric process, also the ocean observations. But at a fundamental level, we have to link research to operations and applications. We have to strengthen basic research, education, and capacity building. And this requires a very coordinated strategy of interaction with the water community, agriculture, transport, disaster management, defense, and so on. So with this, I would like to come to the end of my talk. Thank you very much for your kind attention.
Thank you very much, Dr. Krishnan, for such a wonderful talk. You have touched almost everything that can influence the monsoon in our country. And you have amply described how complex it is to really predict, and you are venturing into, in fact, you are leading the predictability activities of our nation. So that's really great. And I thank you for delivering this lecture. And as we had discussed, without involving a lot of mathematics, which you have done that. So thank you so much.
Yeah.
And I'm sure there will be many questions, but I will request my colleague, Dr. Narendra Oja, to kindly conduct the question answer sessions.
Yeah. Thanks a lot. Thanks a lot, Professor Deshpande.
Thank you, Professor Deshpande. So after this wonderful talk, let's see how many questions are coming up. So there are many comments of appreciation showing up on the YouTube channel that also we are going to take up with the speaker. But before going to that, I would like to request the participants to raise their hands and speak to the speaker directly. So Professor Anil Bhardwaj.
Thank you, Narendra, and thank you, Dr. Raghavan, for excellent talk. It was really informative for me too to understand the intricacies involved in prediction of such a complex system. What I understood from your talk is that by 22nd century, we would expect about 2-degree change in temperature, right? Which is being predicted by all those 5 model predictions, right? And that would also mean that there will be increase in the rainfall. by about 20%, 10 to 20%. Now, what we have been seeing is that when we talk about monsoon, we say the last 100 years of average. And then over that, we say whether the monsoon will be normal or deficit or will be more than the normal. Do you think the time has now come to better classify that average of 100 years to last 50 years or so? Because there's already a gradual change which is happening with respect to what has been seen, as a part of large-scale monsoon and the climate change.
Yeah, I think thanks a lot, Professor Bharadwaj. I think you raised a very important point. In fact, right now, this is a discussion that is going on in the IMS WhatsApp group. Because earlier, the normal was taken from 1961 to 2010. And recently, they revised the normal from 1971 to 2019 or something. So they have, because the mean has reduced slightly. And so the question is, of course, the one explanation is that this is due to the internal variability, there are decadal timescale variations and so on. But the assessment that we are also seeing from a climate change perspective is that anthropogenic influence like the aerosols have also contributed, primarily from the northern hemisphere, and they have influenced the precipitation. So there is a role of the natural variability, but the human influence signatures are also there on the precipitation change. Now, the question is, do we have to revise the mean? I'm not sure whether we should revise it. So the problem is, the thing is, because if we are going to reduce, if the aerosols are going to be regulated, because in the Europe and North America, due to the emission norms, they have cut down the aerosol emissions. And many places, especially the West African region, West African monsoon has slightly recovered after the 90s, partly because of the reductions in the aerosols over these places, and also due to the continuation of the global warming, plus the decadal variability. So if the same thing is happening over this Asian region, we could also see an increase in the precipitation. Anyway, GHG is going to continue. So I'm not sure whether it's a good idea to revise the mean. I think we should keep it and see what is really happening in the future, and how to build the projections, keeping the fact that climate is going to change and get warmer. Yeah, so that would be, of course, the problem is there are two things. One is the statistical model and one is a dynamical model. And we both are combined for various practical reasons. So there are practical issues, but from a scientific perspective, I think I would prefer that we should not be tinkering with the long term. Just leave it as it is and try to understand why it has happened and how to improve the prediction.
Thank you, Raghavan. And can you allow me to ask a supplementary question to this?
Yeah, sure.
Okay, so another thing is that we now see a very large variability across India, in different regions, the rainfall is drastically different. So how good we are in terms of predicting the variabilities and the rainfalls in varying geographical conditions over India?
Yeah, I think that's a key question. So the variability has increased. You have really hit the point. So in terms of the short term, when we look about 3 to 5 days, our predictions especially has improved for the tropical cyclones. We are because they form over the oceans and they are moving towards the land. So we get some lead time. So we are doing a pretty good job. But when we are talking about heavy precipitation events, and especially ones that are leading to flooding, I think there is still a major scope. We need to improve, maybe up to day one. Even the day one forecast, in terms of the rainfall amounts itself, there are big issues. One of my colleagues was showing about the Kerala heavy rainfall in 2018. So nowhere, I think the amounts, even for the entire state of Kerala, A one-day forecast itself, the amounts don't match. And so these are the issues, how to capture the extremes. So, and one thing is, of course, we need, as an initial value problem, your initial conditions have to improve. So maybe improving the assimilation of radar data, reflectivities. Now there are so many Doppler weather radars. So if you can have better values of the vertical velocities and so on, probably we may make some progress in that direction. So how to get the extreme rainfall amounts, how to increase that in the model. Resolution is one thing, but resolution alone is not going to solve the problem. Because we have, as I said, the organization of the convection, getting the large scale. Within the large scale, all these embedded systems are developing and they are interacting. So unless we do improve there, it's going to be very challenging. A lot of work is needed. That's why I said a lot of research is needed on that. And it has to be linked to operations.
Thank you. Thank you very much.
Thank you very much.
So thank you very much, Dr. Krishnan and Professor Bharadwaj for starting today's interaction session. So next we will go to Professor Pallam Raju.
Thank you, Dr. And Krishnan, it had been a wonderful talk, a lot of information. Thank you for that, first of all. I have two questions. One is in terms of the Uttarakhand, water event, wherein you said that the couple of events, the Tibetan, anti-cyclone became active and it kind of colluded with the MCCs forming, and then there was a huge downpour. So that also means that now, from IITM or from the IMD, the predictive group should be also looking at the Tibetan systems nowadays, so that this kind of event can be predicted in the future. Are that's going on? Or?
Yeah. Good. Good, Dr. Pallam. Very nice to see you, and thank you for this question. I didn't show that slide. In fact, I had one. So our extended range prediction group, they did this forecast for the heavy rainfall. So two things was they were able to get heavy precipitation, but nowhere close to the magnitudes. And from their abstract, what they found was the mid-latitude effect was underestimated in their models. They could get some signature of the low pressure systems. They used two resolutions. One was a T126 and another was a 384. I didn't show that slide today, but the models captured some aspects, but still major limitations. When you compare with the observed rainfall and the observed circulation anomaly, there were differences, substantial differences. And the mid-latitude effect was kind of underestimated in the model. And so we are focusing on that. And in the real time also.
Okay. The other question is in terms of the volcano eruptions that you said, that it takes one more year or so after the eruption for the La Nina to get affected because of the volcano. So now that we have a volcano happening, in January, this Tonga volcano. So are there any predictive models of how that will affect the rainfalls in the coming year or two?
No, I don't think right now the operational models are, maybe UK Met Office or ECMWF may be doing it because they may be assimilating. So we need to get the data of the aerosols to initialize the models. And definitely the impact of the aerosols on the radiative fluxes will be affecting the temperature. So, so during the assimilation, that they will be definitely incorporating. And because they do it every 3 hours, they keep assimilating, the assimilation cycle will be going on. So as the aerosols enter the stratosphere, they will be affecting the radiative fluxes. So they will be affecting the temperature profiles which are going in the observations. And but my question is, in operational, but I don't think we are doing it here. That is one thing. And Tonga itself, it was not a very big eruption. It is nowhere comparable to Pinatubo. So we need really massive eruptions like the Pinatubo, Krakatoa. So
okay. Thank you very much. There are many more things to discuss, but I think There are many more raised hands, so I should.
Thank you, Dr. Pallam.
Thank you.
Great to see you.
Thank you very much. So next we will go to Professor Devabrata Banerjee from PRL.
Yeah.
Nice to see you again, Professor Krishnan. I found your talk very interesting. And I have many questions actually, because I came across so many concepts, even though I'm not an expert in this area. The first question is regarding the major unknowns in experimental observations, which can actually help constrain the increase in temperature due to these greenhouse emissions. So, for example, as Professor Sarin in the 90s started an aerosol program in PRL, where he looked at the chemical composition and the kind of forcing which aerosols would have basically in these models, the GCMs. So that was one program. Is there any experimental parameter which needs to be studied in this decade and in the following decade? That is my first question. The second question is which are the satellite observations which are necessary? If one were to, for example, meteosite, you showed an observation. Is it sea surface temperature? Do we need to know it more precisely? Are there any other observations which are very necessary, from a orbiter platform in space in the next 2 decades, which India should have, which will constrain the GCMs once again? This is my first question. The second question is related to the frequency, the increase in frequency of Arabian Sea cyclones. So we've had Taukte, as you will know, and Nisarga, which hit Gujarat and Maharashtra. So why is there, scientifically, is there an increase in the frequency of cyclones? Typically, we knew Andhra coast and West Bengal and other places, Bangladesh, they used to have many cyclones. But is there an increase in the number of cyclones along the Arabian Sea coastline? And should we worry about it in the next 10 years or so? And the final question was regarding the prediction of sea level increase. Is there any prediction of sea level rise along the Indian coastline, which is huge, as you know, from Gujarat all the way up to West Bengal? So when do the increases in sea level in India become significant so that you need to move masses, which are residing along the coastlines? Thank you again for the talk.
Yeah. Thank you, Professor Devabrata Banerjee. Yeah, great to see you. And you have raised all very important questions. So your first question is what kind of observations you need to constrain the model. Yeah. So, okay. And then what kind of observations the satellite should be making? That was your first question. So so from the point I was showing the rainfall over the Indian region, the west coast rainfall, the Western Ghats especially, the rainfall is not from very deep clouds. Now people have shown this. Unlike the Burma coast, Myanmar coast, where the clouds are much deeper, here clouds are not very deep, but the rainfall amount is very high. Even the Western Ghats, rainfall amount is very high, but the clouds themselves are not very deep. So there is and the flow of moisture also people have studied. It's a more gentle slope. So the Western Ghats slope is more gentle. So there's a continuous flow of moisture from the Arabian Sea. It gently rises, clouds form, not very deep clouds, and producing precipitation. And then I think the formation, the aerosol might, the way the aerosols and clouds interact there and produce the warm rain processes, I think that's an area not well understood. Probably that is one area where we have to. And also, how is it different over the Myanmar coast? That would be an important problem. And now, with respect to the observations from the satellite, no doubt SST is very important. And also, so the thing is, the type of precipitation radar which TRIM had, which started in 97, 98, I think we should do it from India also. So that, because you are getting the 3-dimensional structure, you are going to get the heating. So that will be very, very important. Getting the So having a radar on the precipitation radar on the satellite will be very interesting. So that is one important thing. And the second thing is water vapor, because as I said, the immediate thing, the consequence of climate change is increase in the water vapor. And water vapor is going to fuel all these. That's going to be the main energy for tropical cyclones, heavy precipitation. And so we need more water vapor observations. And that is going to be the key. And for example, within a cyclone, how does the water vapor increase? So can we measure that? That is going to be, because that is going to be the fuel for the, so we are good in predicting the track of the cyclones. Intensity prediction is still a problem, not only here, even worldwide. So the intensity is a much more complex issue. So probably this is where I think the assimilation of the water vapor observations will become important. And getting the circulation itself, we need the vertical profiles of the circulation. And now the European Space Agency, they are having a LiDAR in the satellite, which they are assimilating. So that people are thinking that may be a big breakthrough for especially the tropical cyclones and tropical weather prediction. So getting the vertical structure of the winds from the satellite will be a very important step. I mean, these are my points. And then your second question was on the Arabian Sea cyclones. Yeah, Arabian Sea, nowadays we are seeing quite a few increase, which was kind of rare earlier. And generally during the pre-monsoon time. So one thing, SST has definitely increased in the North Indian Ocean, and sea surface temperature has increased. The ocean has also been warming, even below the ocean. So but that is one of the criteria. It also is going to depend on the vertical wind shear and several other humidity in the Mytroposphere and so on. Several other parameters are needed for the tropical cyclone genesis. And it also depends on when these South K and other systems were formed, Nisarga. It also depends on the flow pattern during those times. And probably whether this is due to climate change. Some people have projected that there could be very extremely severe cyclones under a climate change over the Arabian Sea. Yeah, but we need, whether it's a scientific assessment, what is our confidence, we still don't know. But we do see, yes, you are right, that the number of cyclones are becoming more frequent. But whether we can attribute it to human influence, I think that assessment is not yet done. And our confidence is kind of low or moderate. Even very severe cyclones in the Bay of Bengal also have increased. Yeah, post-monsoon season. Yeah.
So thank you, Professor Bennett. And now we will go to the next question is by Professor Lokesh Sahu.
Yeah, thank you, Krishnanji, for very wonderful talk.
Yeah,
and my question is in particular about the ARC exchange processes. And as you know, that ARC exchange is a very, very important source of many reactive trace gases. Of course, you talked about the role of aerosols. And the exchange of reactive trace gases, what I mean is monoterpene, isoprene, and DMS. And among the aerosols, that marine organic aerosols, they are very, very important because they are very efficient kind of ice nuclei, act as a ice nuclei. And as you know that the measurements or studies of these gases over the Northern Indian Ocean, particularly Arabian Sea, which is very, very productive ocean compared to other parts of the world. So how much, because given in gap of data and uncertainties, how it impacts the kind of prediction of a monsoon in terms of their role in ice nuclei?
Yeah, Dr. Lokesh, you have asked, you put me in a tight corner. Yeah, so one thing is one of our colleagues, Dr. Anup Mahajan, so he is involved in this halogen chemistry, trace gas chemistry, and he goes to Southern Indian Ocean and he has made some measurements of all these reactive trace gases. And he is also looking at dimethyl sulfide, which is one of the, through this biological activity, this is produced. And it has implications for formation of clouds, especially the DMS. And he has made some computations of the DMS radiative fluxes, how much is the radiative forcing due to the DMS, and which we want to put in our model and see how it is going to do. So that's a plan. And we have not yet come to the North Indian Ocean, just not to that extent of how it is going to affect the monsoon and so on. It will be much more preliminary. What is the impact of the DMS radiative fluxes on the sea surface temperature, on the in the model? So we want to do that preliminary analysis. So this is in our plan.
Yeah.
So
Thank you,
with
Krishnan.
model group and with Anoop's expertise,
Yeah.
so that's what we are thinking.
Yeah. Thank you.
Thank you. So now we will go to Professor Deshpande.
Yeah, thank you. Dr. Krishnan, I have a couple of questions. First question is that between the AR 4, 5 and 6, how has our understanding about the aerosol has improved? Because we were in a state of ambivalence, whether it would result into more rainfall or less rainfall. But today you have shown in this that the aerosol is balancing the increase in temperature, and then it is also you showed related to lower in temperature. So
Yeah.
can you please comment on it?
Yeah. So I think there has been a big progress in the understanding of the aerosol impact on the climate and the so in fact the SPM statement that aerosol has masked a significant part of the global warming, that is one very clear message that came out from the AR6. So the global mean temperature itself, it has that is a very strong statement coming from the AR6. And the other thing on the water cycle and the precipitation. So earlier, I think the confidence was very low, hardly anything. What is the impact of aerosol on the precipitation or the monsoons was hardly, there was no mention in the AR4 and 5. Now we have come out with very clear statements, its impact on the different regional monsoons. And so that's a special, and also the confidence levels are high, high and medium, depending on the region. So the attribution of the aerosol impact on the climate and the water cycle has substantially improved, that I would say, in the AR6. And this has come because of the what is called as a detection attribution MIP. We call as a DA MIP experiment that was specially included in the AR6. So because of that, many groups could do this DA MIP runs, and that has enabled this understanding, which was not there in the earlier part. And also earlier, what was happening, different models, the way the aerosols were treated, they would start from the emissions and do the same experiment, and this varied across models. And I think AR5 also gave, the CMIP5 models also gave the concentrations of the aerosols. In the AR6 now, they have given directly the aerosol properties. The Max Planck group has developed. They told all the groups can make use of these optical properties of the aerosols, and all the groups use the same, same set of experiments. So that has really improved our understanding, our confidence. So because all these groups have to do the same experiments, that's very important to come out with very clear assessment of the phenomena and its impact.
All right. My next question pertains to the temperature trend. The same again related to 6th assessment report. The first slide actually, when you showed, apart from the major increase in temperature post 1850, I was equally interested in your comments about a declining trend in temperature between 1000 to 1850. So that figure shows a clear declining temperature. So did climatologists focused on that also, that what happened, what was happening at that time? Temperature has come down in your figure.
Before 1850, is it?
Yeah, from 1000 to 1850, there is a clear trend in decreasing temperature. Because that time period is, I think it is quite interesting, because during that period, there was no anthropogenic impact. So all that was happening to precipitation could have been directly related to only natural processes.
Yeah. So as part of the PMIP, Paleo Model Intercomparison Program, people have done these long runs, seeing the effect, to see the effect of the orbital forcings and the volcanoes. And so during this time, I don't know whether it was, you call it 400, that was about 200, 300 years, 300, 400 years before? Was it the Little Ice Age you are referring to? Yeah. So there are some studies which have mentioned that it may be related to the volcanic activity, but I think it must be assessed somewhere in the not in our chapter. It must be assessed. They were not really part of the CMIP-6 experiments. So this is prior to 1850. There is a paleo model intercomparison program. So PMIP-4. So all these experiments were done, effects of orbital forcing and volcanoes and so on. So I am sure they must have looked into this.
Okay. One more question, that when I try to study your talk in holistic manner, you have touched upon various things like land ocean contrast or latent heat, teleconnections, large scale drivers, MTCs. But then towards the end, you also mentioned that there is a definite stochasticism. So how do we take care of random processes in predicting? So could you please comment on that?
Yeah, stochasticity. Now, this is how to do. One thing is we do many realization. Now, instead of, for example, the volcanic eruption, now we want to see what is the synchronization between the El Nino and monsoon, whether the phase is going to. So typically you need hundreds of realizations. So we had something like 140, 150 experiments. Starting from, we started with different states. Suppose you start from a El Nino type of initial condition. You start from a La Nina type of initial condition. So you start with a neutral type of initial condition. Okay. So you have to account for all this stochastic behavior of the coupled system. So as many realizations you have to have. So one experiment with volcanic forcing and with starting with a certain initial condition of both the atmosphere and ocean. The other one also with volcanic forcing with the same initial condition. Only forcing is different. Do like this, a pair of, we call it a digital twin. So you need to have this pair of experiments and compare member to member. You have to compare identical members, only differing in forcing. So then you will be able to filter out the signal. And that is one way. So to get the statistical significance, you need many members. So that is one way to get some idea about it. Of course, it's a kind of brute force method. But so that is one way to get it.
Thank you very much. I have some more questions, but I think in the internet there are many other hands raised, so we will talk later.
Yeah.
So thank you very much for answering these questions.
Yeah, so we are kind of nearing end of session. So, but I will still go to one or two more quick questions. So, Professor Rastogi, please make your question.
Thank you, Naren. Hello, sir. First of all, thank you so much for such a nice talk, as expected. So my question is also related to interaction of monsoon and aerosol, and you partially answered while answering Dr. Deshpande. So when we say aerosol, so in your this model, you consider as one entity as aerosol, because we know that there is a huge size range in aerosol. And then there is a large composition, and then that composition also changes as it remains more and more in the atmosphere. So how do you consider all these things together in modeling?
Yeah. Actually, let me tell what we did at our center. What we did was we have directly given the aerosol optical properties, the AODs and the single scattering albedo and the asymmetry parameter provided by the CMIP-6 modeling group. And that's what we prescribed they've given for different wavelengths. And so we have a three-dimensional distribution of these optical properties, which we have performed, which we have used it, and we conducted. So we did not start from the point going from size distribution, getting the concentration, then getting the optical. We did not do all those directly. We gave the optical properties to the model.
Thank you.
Thank you. So, Mr. Akash, please go ahead and ask a short question, and then.
Thank you, sir. Thank you for the wonderful talk. So, my question is pertaining to the AIML perspective of things. So, in prediction of ISM and its rainfall variability, so far in the AIML perspective, the models that have been are completely data driven, and essentially they do not imbibe they're more black box like, essentially speaking, that they do not imbibe the underlying physics in it. But in other fields, like in theoretical physics, there are physics-informed data-driven models where essentially you can solve the partial differential equations along with the neural network kind of architecture. So, so my question is, why in this particular field, to the best of my knowledge, such models have not been developed or are not in much existence?
Yeah, thank you, Dr. Akash. Actually, I'm not an expert in AI, but you are right in a way that many times people are using, at least in our field, more like a black box, these tools. And but one thing, probably we have to define the problem, what we want to do. Now with, for example, if we want to say that, okay, latent heating is a thing that we want to improve. Now, from the satellite data, we have estimates of latent heating, and the models are not doing well. Now, can we use the AML and use the observations data to improve the latent heating in the model? So, unless we define the problem, it is going to be challenging. If we want, because it's a very complex system, and if the problem is not very clear, if we apply the technique, I don't know, so we may be lost. We may be totally lost. So I think we have to really understand what is the problem, what are we looking for, and then you apply that. So probably that's the way to go about. So we have to really go step by step, one step at a time, and addressing a very complex problem like a monsoon, it's going to be really challenging. And I think it will take a while. And it's not that people were doing this AI and they were using artificial neural network, they were calling it some other. So now it's all packaged in a new bottle, okay, old wine in a new bottle. So it is also, now we are lost into so many jargons and techniques also. That's also one of the things. And now they are telling there are some physics guided AI/ML tools, physics guided tools, that also people are using that. But I think still there's a long way to go.
Sure. So thank you, Dr. Krishnan. So with this, we kind of end the online like WebEx portal question interaction session. And the another portal where we were live is YouTube. So from YouTube also, many senior researchers from the field, they are attending us our seminar today live. So I will read one or two questions from there. So Dr. CBS Dutt, formerly from ISRO, so he has written some appreciation for you, which I am skipping to save time. I will directly read the question. So he's asking, is it possible to work out greenhouse gases emission reduction due to Indian forests as figures are becoming available?
As what is becoming available? I didn't get it.
As more figures and data are getting available. So
yeah, I think it is possible to work out. I think it is possible, and already I think there's a group that is working on carbon cycle at IITM, and so they are finding all these, what is the emission inventory, what are the changes in the carbon dioxide fluxes, and so on. I think we should be able to estimate it.
Okay, thanks.
Yeah.
Another question from YouTube I am reading is from Dr. Manish Tiwari. So what percentage of moisture is supplied by the southern hemisphere from where the monsoon winds originate?
Yeah, it's a good question. Yeah, by southern hemisphere, actually South Indian Ocean is a very vast area. Now the thing is, much of the so probably coming deep from the southern ocean, maybe, I don't know. So it may be varying. We have to really see that calculation. But mostly it is coming from the equatorial Indian Ocean and maybe little south of it. If you go too much, I don't know how much is really coming from that part of the ocean. And some people are even looking at Bay of Bengal and Arabian Sea. They may be having important contributions. So
as
I don't have an answer. Yeah.
Okay. Thank you, Dr. Krishnan. So as we are running out of time, I would like to thank Dr. Krishnan for very patiently taking so many questions from the audience. And I will hand over the portal to now my colleague, Dr. Vineet Goswami, for further proceeding.
Thank you, Dr. Narendra Oja.
Thank you very much, Dr. Narendra Oja, for nicely conducting the Q&A session. And so that brings us to the conclusion of the 39th episode of PRL Coherence Vyakhyaan. So before I proceed, I would like to thank Professor Krishnan Raghavan for accepting our invitation and giving an excellent talk on prediction of Indian monsoon in response to a changing climate scenario in PRL का Amrut Vyakhyaan. Also, we are thankful to him for answering the audience's questions after the talk. Second, I would like to take this opportunity to thank our audiences on both the YouTube and WebEx platforms. Next, I express my sincere thanks to PRL Director Professor Anil Bhartwaj, Dean PRL Professor D. Pallav Raju, and Chair of PRL का Amrut Vyakhyaan Committee Professor Nandita Srivastava for all their support in organizing this Vyakhyaan successfully. I also thank my colleagues in Vyakhyaan Organizing Committee for successfully conducting the 39th episode of PRL का Amrut Vyakhyaan series. I sincerely thank you all for being part of the Azadi Ka Amrit Mahotsav and PRL at 75-year celebrations. Kindly visit our website and our other media platforms to know more about upcoming events being held at PRL, particularly PRL Ka Amrit Vyakhyaan. With these words, I would like to propose the closure of today's episode of PRL Ka Amrit Vyakhyaan. Thank you very much.
Yeah, thank you, Dr. Vineet.
Thank you
everyone.
Thank you.